You don't see what I see, do you? There you go. All right, jump back to where we were. CSTN 283, March 8th, part 2, heat gain. Back up here, I went too far. All right, so we talked about heat loss and doing the calculations for both conductive and convective for getting our total heat loss. The next thing we have to do is actually talk about heat gain. And fortunately, you don't have to redo the calculations. The only thing that changes when you're doing the conductive heat loss and the conductive heat gain is your delta T. But your delta T is going to be from inside to outside. So you're going to be losing it's your cooling load. The thing with heat gain, it has all of those same components, the area of the exposed building, the thermal resistance, and the air leakage. But there are some other factors that contribute to heat gain, including solar heat gain through the windows and doors. And for heat loss, and when you're performing a heat loss calculation, in most all the programs, at least the simpler ones, the Manual J and the ones that we're talking about, the heat loss calculations do not take in any consideration any type of solar effect at all. The heat loss calculations are performed assuming that we're getting most of our heat loss in the overnight period. That's when we talk about that 10-hour period. But we get, inversely for heat gain, we get a significant amount of solar gain during the day, and so that has to be attributed and accounted for in the heat gain calculations. The other thing is occupant heat gain. So depending on whether somebody's at rest or at some level of activity, an occupant can put off anywhere from 250 to 1,715 BTUs per hour. Normally not a big deal in doing any kind of heat load or heat gain calculations for a residential building, but if you talk about occupant heat gain in a commercial building where maybe it's a large sports arena or a gym, it can make a significant difference in the cooling load. So it has to be accounted for. You get 50 people in a gym exercising and they're putting off 35,000 BTUs per hour. That's a pretty big deal on the cooling system. And we'll talk about that too. And the moisture is another big deal for the cooling. What they call cold mass heat gain, and these are all those things that we talked about that also suck power. Not only do they suck electricity, but they also add heat. And we're talking about a building with a significant cooling load. These can make a pretty big difference. And it's anything from the computers to office equipment. And then we did mention lighting gain earlier, and the type of lighting that we use and how much lighting that we use can make a big deal. The other thing we talked about in lighting gain, I think last week, was the one building that I mentioned. They got excited about energy efficiency measures, and they were going to save a bunch of money by putting in CFLs, and actually did use that very spreadsheet that I showed you earlier on what was going to be more cost effective, and they replaced I don't know how many hundreds of CFLs, and they realized that the money they saved on their CFLs they lost because the incandescent bulbs were contributing so much to their heat gain. They were actually keeping it warmer in the wintertime. So similarly, how we get heat gain, a lot of the same areas that we lose it, but as we just mentioned, it's the conduction through the doors, windows, and walls. We do get a significant amount of solar gain through the glass. and then the lights and the equipment and the people. And then the last part, also too, cooling required for ventilation, just like we talked about in the heating. We've got to have that fresh air that's coming in constantly, and that can be a pretty big, depending on the size of the building and how much air we're bringing in and bringing out, that can be a pretty significant amount of air that we need to cool. So when we talk about cooling systems and cooling loads, you will hear these terms fairly frequently. It's sensible heat and latent heat, and you probably had them in physical sciences when you were a kid. And that's what Gary just mentioned, there's a lot of moisture. When it comes to cooling, that's really one of the biggest things that gets missed in the cooling systems is the moisture control. We'll talk about the moisture in a minute, but it's not just the sensible heat in that rise and fall of the air temperature, and it's not just cooling the air, but it's also removing the moisture that's carrying the latent heat with it that has to be accounted for in the design loads. So basic systems calculations and how we do it, I mentioned, and we talked before about the ACCA Manual J. It's the one, probably the most predominant calculation that we see in the residential end of it. It is code required in most areas at this point that a basic Manual J calculation has to be turned in before you can get a permit to build a new house. The goal behind that is to meet the energy code requirements so that you're not oversizing or undersizing your systems. And we'll talk about that too in just a minute. The other part of actually putting those calculations together are the design conditions for the local climate. And as I said, you can find that in a lot of different ways, a lot of different resources. This is just a quick screenshot out of a program called Climate Consultant. This is another free downloadable program. And so you can go in, for example, this one just is from Summerlin, British Columbia. It has very specific weather station data, not just climate zone data, but very specific weather station data. We've got 4 of them, I think, in Missoula, and it's actually interesting how different little microclimates you can have, and whether it's the wind loading, solar exposure, it's not going to significantly change the performance of your building, but it's going to increase the accuracy of your design load calculations and predictions if you use local data. So, and it's an example of a resource, and it's another kind of the same program, and this will tell you this is just a graphic representation of your daily temperature ranges, and so you can see based on hour over hour, day by day predictions of what the temperature is going to be. Most of this stuff, when you start getting into more advanced building modeling software and energy modeling software, most of the stuff will integrate directly into it, and you can look at calculations and predictions of if you put the right information in Monday at 3:15 p.m. on March 15th, you can get a pretty accurate prediction of how much energy usage you should have based on those averages. The good thing is with a lot of those programs, they're far beyond the scope of what we're getting into here. They've been around long enough now, and we've amassed enough data that the predictability of them is really, really good. So when it comes to designing, when it comes to getting things right on the thermal envelope and the heating and cooling systems, we're working off of some pretty good data. So, again, a couple other things in there we've got to look at. So when we do the calculations, we'll talk about this a little more, we've got to look at not just the heat loss, but we've got to look at the overall heat gain. And when we look at the heat gain, we've got to look at both the sensible and the latent. And you understand, and we'll talk a little bit more about it, but it can make such a difference depending on where you are. Obviously, in our climate, we're not really going to have that much of a concern about heat gain. We just don't have a design temperature that we require much cooling, and so it's not going to be significantly important for us. But as you move around the country, that can change dramatically. So went through those. So once we get all of that information, we've done all the calculations, whether we're doing the Manual J or any one of those programs, we've taken our whole building assembly, we've calculated the UA, we've got the convective heat loss, we've got the conductive heat loss, we've got the total heat gain. We pretty much know what the BTU load is of that building, how much energy it's going to take to heat and cool that building. So the next step is equipment size and equipment design. And this is where in the ACCA manuals, it's the manual S for system selection. Excuse me. Now, based on most codes, once you get your Manual J calculation, and then, as I said, it's becoming more and more of a requirement that you've got to turn a Manual J in before you can even get a building permit. With that, it's also in some areas they're requiring a Manual S, and you can't use equipment that's more than 110% of the design load. And well, the difference between oversized systems and undersized systems can be pretty significant. And here's where it depends on a little bit who you talk to. Sometimes if you're talking to your heating contractor and they're talking about sizing the heating unit, they want it to be as large as possible. Some heating contractors just want to make sure they put enough heating in and they put a big enough unit in so you're covered. Oversized systems are probably more costly and cause more problems than undersized systems. And a lot of, when we're looking at high performance and sustainable homes and larger buildings, a lot of mechanical designers and heating contractors are starting to design functional inefficiency, and by that I mean they're designing about 10% less than design load. Remember, when we went through those basic calculations in design load, based on the design temperature, we were really looking at preparing for the worst 4 to 5 days of the year. And so if we've got a system that is just slightly undersized, it more likely than not is going to cover us even in those worst case scenario days. If we've got a system that's too big, there's actually significant risk and detriment to occupant comfort. So not only is the equipment more expensive, larger equipment, larger air handlers is going to require more ductwork, potentially have higher electrical loads and requirements. But the biggest part of it, especially with forced air, is larger equipment tends to short cycle. Because it's larger, it's going to come on. It's going to come on just for a short period of time, and then it's going to shut off. And while it may do its job, the thermostat calls for heat, the heater kicks on, it quickly brings it up to that temperature. It may not provide the best occupant comfort because all that heat's not necessarily going to distribute evenly around the house. It's going to be short bursts of hot air, and the heating system is just not going to run for long periods of time. especially if you've got your heating system integrated with the heat recovery ventilator and bringing fresh air in, now you've got oversized equipment that's not running for very long. So if it's tied to the heat recovery system and the fresh air intake, it's not pulling fresh air in either. So more and more we're seeing good, responsible heating contractors. They're designing at design load or about 10% less than design load. And it's harder on the equipment, is the last one too. You think about it like a car. It's a lot of that start-stop driving is far more detrimental to your engine than getting on the highway. So we talked about the sensible and latent heat specifically, so we could talk about air conditioning. And AC has two main priorities. And the first one that everybody knows is lowering the temperature and cooling the building off. But the second one that's almost as important is lowering the indoor humidity. So you think back to that slide, we talked about humidity and comfort and how if there's too much humidity when it's hot, it's going to make you even hotter. And if there's too much humidity when it's cold, it's going to make you colder. Especially when it's hot in an AC system, it's got to be designed so that it runs long enough to lower the humidity. So have you guys, did we talk about tonnage? And it's just another, when we talk about cooling, a furnace is usually rated in BTUs per hour. It's going to be an 80,000 BTU capacity furnace or 50,000 BTU capacity furnace. Air conditioning units are sized differently. They're sized by the 12,000 BTU increment, and they call that a ton. So, and I know what you're going to say. Well, it's the same measurement. It's BTU. Why don't they just keep them all in BTU and keep it simple? Because that would be too easy. So I'm sorry. What's that?
Because one guy understands it this way, and the other guy understands it that way.
I know. Well, they do. You know, we'd be out of work if it was really simple and everybody could get. No, I'm kidding. All right. So, basic concept of cooling systems, and the biggest part of this that I want you to focus on. We're not going to spend too much time on it, but working on the refrigeration process. But what happens is blowing that warm air across the colder coils, and by doing that, not only is it cooling off that air, but it's taking the moisture in that air and it's causing it to condensate. So it's also pulling that latent heat out of the air and reducing the humidity, and that's what makes the air conditioning unit work. Does that make sense? You guys all understand that? You've been passed through that before? All right. So one more quick note, just an example. The other thing that you'll see a lot, and it's why I think they are requiring more and more of the load calculations as part of permit. There are a lot of rules of thumb in the industry, and most of them don't work. And for years and years and years and years, the rule of thumb for cooling was you need 1 ton for every 800 square feet of house. And heating contractors, for the better part of 20 years, I listened to heating contractors talk in that manner. And so I'll give you just a quick example why it doesn't work. But 2 identical houses, 3,200 square feet, climate zone 1, very high humidity, very tight construction, really good high performance building envelope. One's on the south side of the lake and one's on the north side of the lake. And they both have all of their windows facing the lake. So you have 2 houses built identical. The one on the north shore is facing directly south, and the one on the south shore is facing directly north. They're facing each other, but it's far enough away they can't see each other. So it's in climate zone 1, so it's in a hot climate zone, predominantly cooling season. We've got very high humidity, very tight construction, and a good envelope, and one of them's facing due south and one of them's facing due north. Any observations that you can think of?
South face. The one facing south is going to be less humid than the one facing north.
One facing south is going to be less humid than the one facing north.
Well, if it comes to orange, yeah. Typically.
I'd buy that, yeah. Anybody? What's that? They're both, one sitting on the south shore, one sitting on the north. The lake's right in front of the houses.
One facing south.
They're, it's north, due north and south. Is
I'm
that?
thinking of a reflection of the heat off of the
Yeah. Well, think about it in terms of heat gain and cooling and sizing and sizing a cooling system.
sun coming in the south side.
So, right, the one that's got all the windows facing on the south side is probably going to have a significant heat gain. And what's going to happen there? What could potentially happen there, I guess? Higher requirement for energy, larger, so the rule of thumb was same heating contractor did both of them, and he said, nah, I've been doing this for 20 years, 800 square foot per ton, you both get a 4-ton unit.
And this guy's burning more than that guy.
Yeah, so think of it in terms of heat gain. The house that's on the north shore that's got all the windows facing south is going to have a significant solar heat gain. And there's a good chance that the 4-ton unit might not be enough if he hasn't done a heat load calculation factoring in all of those windows and the exposure that house has. And what about what's that?
And the 4-ton heat unit in the north may be too much.
It may be too big, and it might come on and cool the place down really quickly, and then what? We're in a really high humid climate.
Cold, humid.
It's not gonna run long enough to get the humidity out. So the guy in Mr. South or Mr. B, his unit's fine. It's large enough because he's not getting very much solar heat gain to lower the temperature, but it's oversized, and so it's not running long enough to control the humidity. So he's going to keep turning his thermostat down, and his house is going to end up being freezing cold and damp.
Yep.
And the guy on the other side is going to cook because he's never going to be able to get.
He's buying curtains.
He's buying curtains, and he's going to lose the view of his lake. That makes sense? Yes, no, maybe so. So last thing is much more popular now is the hydronic and system design. The heat load calculations and we are using hydronic almost exclusively for heating. So you're not going to be worrying about heat gain. The heat load calculation is done exactly the same for the building and the envelope. It's just a matter of then once you find the design load, you've got to be able to deliver enough heat through, whether it's hot water baseboard or radiant infloor. And the simple calculation for that is just based on what's your system temperature change, gallons per minute, and then 500, and 500 is what the BTU load is for a gallon of water. And that is just as the ACA Air Conditioning Contractor of America, they have the manual J, S, and D. The Gamma H22 is the standard that's used for sizing and delivery of hydronic heat and equipment. Any questions on heat load, heat loss, heat gain calculations? Does it make sense? It's science. We can pretty much predict how much energy our buildings are going to use. The only thing that really does vary is sometimes the quality of the construction and then the occupant. And what was your answer?
The weather?
The weather. Well, yes, the weather. But you know, with all the data that we have with the climate consultant, and we've got decades of averages that give us a pretty predictable model. What will happen to the weather over the course of the rest of our lifetime, I'm not sure, and it might get hotter and hotter. And yeah,
Everybody's gonna cool the house so much, they're gonna cool outside.
I don't know. Any questions, let me know. I think there's still one or two folks I got to get the quiz out for, but we'll handle that, and I will see you all next week.
So, I was thinking about the heated discussion we had on the heat questions.
Yeah.
And I was also thinking that, when is it? You probably were pretty much basically right. But I was also going to show you that it's not about understanding and answering the question right. I understood it, I just over-understood it.
You thought too much. Yeah.
Not too much.
That's part of. If I can impart any knowledge on you through this class whatsoever, is
That 90.1 does not.
know what you know and don't overthink it. Don't. Yeah. Hey, Todd, do you want to? I might have to print a hard copy of that out for you. Do you want it now, or do you want to get it next week?
If you have it now, I can take it.
Yeah, let me. I have it. I'm just trying to get. I'll come back for this. Let me go grab it.
Okay.
Yeah, I just had to print one out. I think I still have it sitting up on my computer.
Yeah, I'm just putting some in the back. Don't test anxiety. Do that every time. That's why I like to do it twice.
Is it a 1 square?
I get test anxiety so bad. That's why, that's that. Because 60% of students have test anxiety. And they do too intense.
And then you can go.
You can do your,
Yeah.
and then go, and then you go back and you're like, yeah, I got a A in both 101 and 102,
Yeah.
because he's got it set up so if you don't do the work, you're gonna fail, but if you
Right.
do the work, you're gonna pass
Yeah.
with a good grade.
Right.
He's got it set up that way.
Yeah.
But I was bummed that 102 wasn't open this year.
Yeah.
I swear, those two classes were like awesome. I loved it. And actually 102 kind of puts 101 in its place and explains it all. And then at the end, it shows you some hope in the future. And you're like, all right.
Yeah.
It like gives you conclusion of 101. It makes it so much better.
Oh, yeah, well, and I wanted to be able to take it in series,
Like I did. That's how I did. I did 101 and then 102, and it was great.
And it's like, well, now I gotta wait in my last semester to take it, and so I'm not getting.
If you even ever will be able to take it.
Yeah, right.
You know, because they officially stopped enrolling students for our energy tech program.
Pretty cool.
It's official. So, once they graduate us out, there's no more energy tech program. Which means that the ones like us who are still barely coming to the certificate, by next year, it's gonna be a struggle to get to the associates without having substitute courses. It's gonna be difficult. I'm actually considering going to Bozeman. Bozeman, unless you don't mind going to Butte. Me, I lived in Butte for enough years where I'm just like, yeah, I'm not going back to Butte. I know better. It's Butte.
Yeah.
You know, it's not the butt town of Montana for a reason.
Yeah.
But, you know, Bozeman, and especially with my NASA scholarship, I've been talking to a lot of, you know, people up at NASA, and they all say, go to Bozeman.
Uh-huh.
Go to Bozeman. They say, we're hiring students out of Bozeman.
Yeah.
So, I mean, if you want to go like engineering in the energy field, then yeah, I would recommend looking into both of them too.
It didn't print out with question numbers, but I am sure you can figure it out.
Oh, okay.
I figured it out pretty easy.
Yeah.
It wasn't a hard quiz.
What's that?
It wasn't a hard quiz. You just had to, you have to read the book.
I think it's, I think now everybody